one last thing from today is the cause behind the effect. If the effect is the force, the cause is that around any positive or negative charge, you've got this imaginary, well, I say imaginary, but it's an invisible electric field. In which direction do those field lines go? What?
All directions.
Well, they would certainly go out the way, but in terms of positive and negative, do they go negative to positive or positive to negative? Alistair? Yeah, like electrons do. It would make sense, wouldn't it? Well, back in the sort of depths of time when physicists were first working out, they didn't know whether the particles that carried electricity were positive or negative, so they just sort of almost tossed a coin and said, well, we'll call them positive. In time, we found out that it was actually negative electrons. So what's called conventional current, which they teach south of Berwick, is actually what's called conventional current, where if you've got a battery which is positive and negative, then the electrons flow from, the charge in conventional current flows from positive to negative. Scottish educational system is one of the few that actually teaches what's called electron current flow, where current flows from negative to positive. Electric field lines, unfortunately, stick with the positive to negative convention, so you end up with field lines going something like this. So they spread out in all directions from positive, and they come in from all directions for negatives. And you can model that. There's various software packages, either on the net or on Scholar, that you can use to build up what happens if you put various charges in various places and see what happens to the electric field lines. So we've got these imaginary lines, which you don't see. Well, these are invisible lines, which you don't see, but we can certainly see the effect of. The definition of what electric field is, if you take the electric field vector, say here, we say, right, there's an electric field there. What do you think the definition of electric field might be at that point? Oh. With the force, but if you put, say, a charge, if that was charge 1, Q1 here, and this was your second test charge, we'll call it QT, for just something which we've decided to put there to see if there's an electric field. That's the test charge that's been put there. How would you get the electric field, E, in terms of the force? How is the electric field related to that force then? Think back possibly to what you did with gravitational field. How would you get gravitational field if you knew what the gravitational force was? In terms of that force. Wouldn't be dividing by mass. The radius is difficult because it could be anywhere here, and it might not be a direct line that it's going from there to there. But I would agree that the radius affects the force between those two there. But what we're talking about, we know what the force is, but what's the field? What's the electric field there? Andrew? Yeah, so you divide by the charge. So it's the force not per unit mass, but the force per unit charge. So if you've got a charge of 1 coulomb here, it's the number of newtons for every coulomb that you place at that particular place. So electric field, would you imagine it to be a scalar or a vector quantity? What do you reckon, Aaron? Scalar or vector? Yeah, it's vector because it's got direction. We attribute it to having a direction. So it's the electric field is defined as being the force per unit charge. It exists at a point, even if the charge isn't there. And it's a vector quantity. It's got direction. What would the units be for electric field, given what we've got up on the board? Kirsten, what do you reckon? Yeah, so you're measuring this in newtons for every coulomb because the force is in newtons and the charge must be in coulombs. Lastly, can you get the electric field for a point charge or a sphere out at any distance from the center? Say if we wanted to know what the electric field was due to this charge here, Q, we're moving out a distance r. You could work out that test charge. What would the electric field be because of that particular distance there? Force between the two is 1 over 4 pi epsilon naught Q1 Q2 over r squared. But what would the electric field be? So remember, Qt is just a test charge. It doesn't have to be there. What would be the electric field? So to get the electric field, you divide by the test charge itself. So we're dividing that by the number of coulombs. So you get 1 over 4 pi epsilon naught Q1 over r squared. That's electric field at a particular point, and that would be in newtons for every coulomb, with that being in coulombs, and that being meters. So we've got two equations, two similar equations. Hopefully, they look quite familiar from what you did with gravitational force and gravitational field. That's why we're not spending too much time on it. Okay. But it's this constant permittivity of free space, 9 times 10 to the power 9 for the whole thing, 1 over 4 pi epsilon naught. The reason that the 1 over 4 pi is there is because generally it's to do with a spherical axis of symmetry. So we're going to be dealing with this to do with spherical coordinates. That's where the 1 over 4 pi comes in. Start.